Is there anything I need to do or anything?
Yeah. Welcome back. It's a brand new week, and we're having the embedded Rust class back after the Rustcom. It's haven't been easy, but it has been fun. The Rustcom was really fun. If you didn't attend the Rustcom, I think you should wait for the stream and check out some talks. It was really nice. We're having Professor Brad here back to continue the embedded Rust class. I think we will dive more into the hardware stuff and then dealing with some cool stuff. And then I want to give a very big sorry to everyone for like a break in transmission on Monday. There was no class due to some technical issues. And then we from the Rust Africa team are telling you guys we are very, very sorry. And thank you for understanding with us. Okay, over to you, Professor Brad.
Hey, yeah, sorry. The technical issues were me screwing up with schedules and stuff, and I apologize for that. We will be meeting today here from my lab at home, and then hopefully we'll be meeting next Monday from China. I'm off to GoSim Rust Global in China. Later today I'll be leaving, and so it's all very exciting. Yeah, RustConf was amazing, and yeah, we're going to try to get the videos up from that as quick as we can. I'm working with people to try to accelerate that. Hopefully they'll be up soon. Yeah. So let me flip back to the screen before I forget again. And we will go ahead and tackle some more Rust. And the good news is that today what we'll tackle is actual Rust embedded. I'm glad you're here too, and I'm glad all of you are here. This is super fun for me and super exciting. So let's see if we can figure out some more Rust stuff. As always, if I screw up with video or if things are too small or hard to read or you can't hear or anything like that, please put it in the comments. I'll be watching them as close as I can, and we'll try to figure it out. So let's remind ourselves of where we've been and where we're going here. Again, the URL here is on GitHub in Rust Edu is Rust Africa Embedded, and that is the place where you can find this these notes and all this materials. This is sort of a place. Okay, it failed to post, it says in the comments for some reason, but hopefully somebody can paste it in. Wonder why it failed to post. That's super weird. All right. So let's, yeah, like I say, talk about where we are and what's going on. The first week we covered Rust, and we mostly just covered Rust, and that's great. We needed to get some Rust under our belt to understand what's going on, but mostly I think we're done with Rust. There's a couple topics I skipped last week for time, traits, and error handling that I think we need to talk about real fast. And then we will move, and you know, these are, the traits topic is a huge topic. We're not going to cover it in any detail today. As we start to use Rust traits, I will point them out to you and explain what their deal is. But I'll at least give you a little overview today. And then I want to talk about Rust's error handling strategy, because it's very different than the error handling strategy of other programming languages. And then we'll start talking about actual no standard and all the stuff we need to know for the special environment of Rust embedded, because we're doing Rust in hard mode in this course. We're going to actually Not that it's all that hard, but we're going to actually tackle using Rust without a lot of the things that make Rust easy. And we'll show how to deal with that, and it'll be fine. So let's start with a little bit of Rust trait. Um, all right. So what is a trait? A trait describes an interface. Most programming languages, unlike C, have some way to describe an API, describe a data type and its interface. And what generics do is what traits do is let you use, generics is a whole nother topic that we should talk about probably, but what traits let you do is describe an interface that some data type will follow. So if I say trait doubleable, that's a property an object can have that it's doubleable. And probably the API will be defined by some method. And what is the type that it's going to return? I don't know. It'll be some doubled type. But I'm not going to put a definition here. I'm going to just explain something that obeys the double trait. You can double it, and double it means pass it a reference to the thing and get back the thing doubled. And let's fix that. Type doubled. What type is doubled? I don't know. So now I have a very generic interface. I can implement that interface for some data type. Impl double for U32, let's say. And type double, then I have to say what the type is in that case. This is what's called an associated type. And I have to say what doubling a U32 looks like. I'll do it. I'll write it this way. That's just U32. And what I can say is there we go. We'll return that. Remember, that's our return value in Rust. But I can also implement it for something else. Let's say for string, for a stir. And the double type could be a string. And I could make myself have a couple of make myself double the string, and the obvious way to do that would be to I've been avoiding strings for the most part. Maybe this isn't a great example, but it's okay, I think. We'll make a string out of that stir, and then we'll return s plus equals s, and then we'll say return s. Let's see if this all checks out. I'll probably get some warnings. Well, let's just use these. Oh, come on. And now I can call this double method on strings. I can call this double method on numbers. And both should work just fine because both these things obey the double trait. Oh, cannot find type double. Oh, I didn't mean that. Yeah, be careful. Here, I need to say, no, the doubled from self. Yeah, I was afraid of that. There we go. Oh, yeah, it won't. Let's just do that. There we go. All right. So now we got a thing, and when we run it, it prints 34 and hello. So now we've got this trait, and we can implement it for anything. Well, this is kind of a boring example, but maybe a more interesting example we've already seen, right? There's the debug trait, right? For example, right? Remember that gives us the ability to do debug prints, right? Well, how does this work under the hood? How this works is when the compiler sees this derived debug, it rewrites it as an impl. It says impl debug for S. It turns out debug is a trait. And then it provides a formatting function that's the required bit of the debug trait implementation. Similarly, display is the thing that actually lets you print without debugging. We can implement display for S. We can't derive display, but we can implement display for S. And then we'd be able to display it. The clone trait, right? If I said derive clone, that would let us implement the clone trait for S, and that would be the same as if we said impl clone for S and then provided the required API for clone. So these why are we implement? Sorry, there's a question. Why are we dereferencing self twice for the U32? Because it's being passed by address because this interface is a little weird. And so, this is a reference to self is a reference to a U32, and we need to dereference it. And then we need to dereference it here. I think if I get rid of these, it will actually probably still work. I'm not positive. Nope. Oh, well, yeah, shush. Yeah. Let me comment this out for a second, then we'll try again. Yeah, I know it doesn't. I'm aware of that. Can we really go back to the universe in which this doesn't get in the way of that? Okay, there we go. Yeah, this compiles fine. If you don't dereference these, they're implicitly dereferenced by the plus operator, and so you don't have to do it at all. Oh, you could also say self times 2. Sure, you absolutely could in this case, and it will probably work fine. I just preferred to write it this way. I don't know why. Yeah, absolutely. 2 times self will also work. And again, I don't think you're going to have any type problems, but I would prefer to write it this way probably just to make it clear what's going on. Clippy, I don't think cares either way. Let's ask it. It's fine with this, and it's fine with this. Yeah. Rust implicitly dereferences references at you quite a lot, and so it's something you got to watch out for. Anyway, let's go ahead and just manually implement the clone trait for S. It'll be fun. Let's go look at the definition of the clone trait. One moment, please. Rust trait clone standard. So if you look at the documentation for the clone trait, you'll notice that the clone trait requires that the thing be sized. That's a marker trait. We're not going to talk about that right now. But it has one required method, this. This is what we're going to implement right here. So let's go ahead and just copy paste that right out of the manual, and then explain how to clone one of these. Notice that there's also a provided method. That's a method that has a default implementation that you don't have to write. You don't have to write clone from at all, but you can choose to write your own clone from and override the default implementation. All of this stuff is pretty fancy, and you probably don't need to understand stuff quite so much at this level. The implementation of clone here actually would require unsafe code, but it turns out that nothing's checking that we implement it right. We could just put this in there and it'll compile. Yeah, it's fine with that. But if we ever try to clone it, it's going to go badly. It's going to panic. Yeah, so that's Rust traits very, very fast, probably too fast. But that's the idea behind them. So the other topic I really wanted to talk about, now that we have traits under our belt a tiny bit, is Rust error handling. Because Rust error handling is a little special. So there's this type in Rust called result. And result is an enum, actually. If you were to define your own result, it would look like enum result. And this is Rust's generic types, right? These are types that can be anything. And what we would say is that a result is either okay of some type or error of some other type. And now we have our own result type. And it's that simple. Remember, these are data carrying enums, right? This okay here will contain some value, and this error will contain some value. Now, we don't need to declare this type ourselves because it's already built into Rust. It's part of the language. We'll make up the viz function, which returns some F32 because I don't care anymore. We'll make it fancy. Except, so if we just do this, actually, this should just return U8. I'm not going to mess with this right now. If we just do this, right, then it's kind of error prone, right? Because if I try to print div 12 comma 8, well, 8 goes into 12 once with a remainder of 4 that we're ignoring, so it should print 1. But what if I print div 12 0? Oh, that's going to panic. So if I run this, oh, not so good. Not so good at all. And So now we got some problems, right? Because we'd really like to not just have some weird divide by zero panic. We'd like to let the caller do something about this in the case where it doesn't work. One way to do it would be with an option. Remember, option is another Rust data type that's given us that's an enum like this. So this thing gives you some data if it succeeds, but it just says no if it fails. And that would absolutely be a legitimate way to do this if you chose to do it that way. If D is not equal to 0, else, and we want to put some of this, right? We want to actually return it. Yeah. Let's actually undo this and do it in a couple of stages so we have it for later. We'll call it raw for lack of a better word. And here we just go none, and now we can write something like this. We can use pattern matching again. Quotient. We'll print that quotient. So that's a fairly fancy piece of Rust. Let's walk through it really, really carefully. This let here is going to pattern match. So if div returns something, which would mean that the denominator is not 0 in this case, then we'll print that thing. Otherwise, we'll handle the error println div option 0 bad arguments. There we go. That's probably a good way to say it. So now we'll get a nice little error message if this is a thing. That's great. And let's go. Let's make sure this works. And that's great. Oh, I'll be greater if I got it right. What did I do? Did div option not get? That's super weird. Oh, I see. I left our option type turned on. Right. Like I say, this type's in the standard library, and so you don't want to. Yeah, there we go. And then the other thing was that should be div raw, I guess. So I'll give the same answer here. And this should be div raw. And this should be div option. Sorry. The problem with doing demos on the fly is sometimes you forget things. Spreadmain panicked. Attempted to divide by 0. So notice that it prints 1 here, which it's supposed to. It realizes that div option returned none, so it says, oh, div option has bad arguments, and then it panics, right? So yeah, that's fine as far as it goes. The problem is that it's now up to the caller to interpret what none means. If I'm quite confident that the only thing my function would ever return none for is for some simple thing, if it's like it kind of expected that it'll return none sometimes, the option approach is fine. But it probably isn't expected in this case. I probably expect that I will never try to call this with the denominator being 0. Maybe I'm computing the denominator some fancy way. And so let's show you the real Rust way to do it. So if it's successful, the result is a U8. If it's unsuccessful, we need some error type to return. And in this case, we want to return OK. And let's make an error type for ourselves. We'll make it not that fancy for now. Enum div error. And we'll say that the kind of error we could have is bad denominator. And that bad denominator will actually say what the denominator was. Error bad denominator. So this is going to be div error. Bad denominator of D. Yep. All right. So this should be div result now. Yeah. And so now we've got a thing that will handle this by returning an error type. And let's derive debug for div error so that we can actually print one. And then let's down here, result. And this is OK. And that's great. And let's use a match statement instead of an if statement because we have two cases. There we go. You'll notice it's getting fancier and fancier. If it's an error, we'll print this stuff. We'll debug print. There we go. And so now we have a thing that can either return some kind of error or it can return a value. And those are the two choices. So that's great. And I think this code will compile and run. Maybe not. For some reason, I don't see it. Let's see. Oops, bad denominator. Oh, right. Sorry, my bad. In Rust, as we talked about before, we have to qualify our enums values. And we get some warnings about field 0 being not read, right? And that's just because we're only printing it in debug. And it says, yeah, bad denominator 0. Notice that we could do something fancy with this, right? We could match on this error and handle different errors that we got back differently. That's the beauty of this general approach. One more thing, and then we'll be in a better place. Let's whoops. So we're going to make our own function that indirectly calls div result here. And this one will take no arguments. But it still needs to return probably the same type as div result does. because we need to be able to have div errors or whatever. One way we could do this is like this. And that's obviously silly. If we wanted to process this somehow, for example, we could do that, but we probably don't here. But the point is, this match seems stupid, and it kind of is stupid. Because this result is itself a value, I can just do this, and that's fine. So the thing can go through here. Okay, that's fine. Here's the trick. Sorry, there was a question somewhere? No, it doesn't look like there was. If Q is 1, got 1, and then we return OK of Q. And we could also then just handle the error case this way. And again, now things look pretty gross, but I really want to be able to print the case where I got 1 specially here. And so this will compile and run. Maybe not. Oh. Huh. Consider changing the field or remove the field numbering. Oh, this is just this warning again. What's the error? Oh, it's the panic. It's the panic. That's fine. So again, we get the bad denominator 0 error. But if we change it to this, we'll see got 1 and we'll see 1. And that's fantastic. That code's gross, right? Nobody wants to write this. Nobody wants to read this. How about we clean this up a little bit by getting rid of all this crud? It turns out Rust has some magic. So let's go with the magic here. What I'm going to say is something that looks mysteriously simple. This won't compile quite. I'll show you how to fix that in a moment. But if it did, here's what it would mean. Call div result. If you get back an error, then just return that error from the caller, right? This thing's returning a div error. This thing's returning a div error. It's this question mark says just when you get an error, return it to the caller. Otherwise, get rid of the OK, so you just have a value. Now I can test that value, do whatever I want with it, and when I'm done, I can return whatever I want, right? So why won't this compile? This is actually cool. This is Rust's main error handling mechanism, is this question mark thing for passing on errors in this result type. Let's see what happens. Yeah. Oh, it worked. It did compile. My bad. Okay. I didn't think it would, but that's great. All right. So yeah. I'm gonna get it to shut up about div errors bad denominator problem because it's really driving me nuts. Where's div error? What was the error it was giving? It was dead code. And now it compiles, it runs, and it panics. So yeah, this is Rust error handling. You don't define your own error types. Often the error types are defined by the standard by the libraries you're using, and you just use those error types. In this case, the error type's kind of dumb and boring, but a lot of times in embedded code we'll have very complicated errors, and we will have therefore very complicated error types. And that's all to the good. What Rust doesn't have, right, is exceptions. There is no exception mechanism really in Rust. This is how we handle errors. It has the advantage that if I return a result like this, you basically have to deal with a result, which means that you can't leave out the error handling code. One of the most common mistakes in C is to just not bother to check whether the function returns some weird value that indicates an error. Here, you don't return weird values that indicate errors. You return results or options, depending on what you're doing, that then have to be dealt with because you can't get at the data inside without unwrapping those options. So that's all I think I want to say about that right now, because I want to get on to the fun stuff. I guess the other thing I should say is this, though. Yeah, thanks, guys. The error trait. Core error is a trait. And it's a trait for things that you might want to use as errors. And there are some advantages to making sure that the error trait is implemented for your thing. So we can implement the error trait for our div error, but we're not going to implement the error trait for our div error because it's working fine. Notice that if your thing is debug and display, then you don't have to implement. That's both required to be able to implement the error trait. And if that's the case, you don't have to do anything. All the methods are provided. I'm tempted to show this all off, but I don't feel like I want to spend the time on it. I want to get on to more interesting things. But let me know in the comments if you want to see more. We'll see this stuff all in practice as we start to write embedded code today. And so let's just go on for now. But yeah, I can come back to it for sure. All right, next topic, how compilation works and that kind of stuff. Okay. So let's run our hello world again. If you'll notice that Cargo wrote us a hello world. Let's run it. Sweet. what is this compilation thing? What does it even do? Well, what it does is it takes your source. The Rust compiler is run by Cargo, Rust C, is the Rust compiler. And Cargo runs the Rust compiler, and this target directory we just got here, if I look in the debug subdirectory, I see a thing called no standard, and that's our program. It is an executable program. I don't need to use Cargo Run at all. I can just run this program because it's a perfectly good program. Well, what is a computer program anyway? It's an executable program. It's a sequence of instructions and some data. The instructions here appear to be 64 x86 64, which is also known as AMD 64. It's 64-bit code for Intel and AMD processors and things that are pretending to be Intel and AMD processors. That's great. And that's what Rust is going to build by default on my machine, since my machine and probably yours is a x86 64 computer. Probably every one of you pretty much. Maybe some of you are building on your phones. Those are ARM64 targets, but most of us are going to be building on a laptop or desktop, which is x86 64, I suspect. Yeah, thanks for linking the course outline. I don't know why it didn't let me do that. Let's see. So that's great. That's fantastic. One of the things that thing uses is the standard library. The standard library is combined with our source code to let us do things like call the operating system to print this hello world out. And that's great. That's fantastic. Unfortunately, if we take a look at our little computer here, this microbit that we're about to start building for doesn't have a standard library, an operating system, and so that it can't have a standard library because the standard library wants to talk to the operating system kernel. So with no operating system kernel, we get no standard library, and there wouldn't really be room on this device for a standard library anyway, or the pieces of it we were using. It wouldn't be easy to fit it. So instead, we need to tell Rust not to use the standard library. That is actually doable, and that's what we're going to be doing. So let's talk about what that looks like. Sorry, one moment, please. So let's compile this no-stud. That's all it takes, is I tell Rust, don't use the standard library. Don't link against it. I'm not going to be using it. Don't even think about it. And now when we try to compile this, we'll build it, release, so I get all this debugging stuff. It's like, you know what, though? You called println. You can't call println. It's not a thing because it's not in the standard library. So you can't do that. It's not a thing. So we're going to have to somehow find a way to write our characters to the operating system without using Rust's standard library. Turns out that's doable. We're not going to push it too far here. Let me go look at some source code that I've got. Yeah, this isn't what I wanted. Yeah. This is what I wanted. Here's what a program looks like that can run Nosted on my Linux operating system. And it'll probably run Nosted on your operating system, even if it's Mac or Windows. So let's just grab this code and put it in here. Yeah, it's about time to stop. One moment, please. Whee! So what's going on here? What a freaking mess. First of all, we tell it we have no main program. What does that mean? It means don't use Rust's normal main program. We have a thing called main, obviously, that's going to be our main program, but it's like, no, but it's not Rust's main program. It's our main program. No mangle. That says don't use a Rust style name in the executable for main. Just make it be main like it's supposed to be. Panic handler. Without the standard library, we have no way of panicking when something goes wrong. So Rust requires us to run with a panic handler. And that panic handler there will, in this case, not do anything. It just quits with exit status 1. It doesn't matter because we're never actually going to panic here. But if we did, this is what would get called. Finally, let's look at this code. We get a C string. That is a string that's null terminated. Anyway, it doesn't matter. We get a C string containing hello world. And then we call the operating system. We send that string to the operating system through libc. We use the libc write routine. And we write to file descriptor 1, which is standard out on a Linux box. We write a pointer to the characters. We write a pointer to the number of characters. We write the number of characters. And that is that. Now, will this build? Unsafe attribute used without unsafe. Oh, that's new in Rust. Thanks, Rust. That's new in latest Rust. And then it's like, yeah, no. Panic equals abort would be a good idea, it says. All right. Let's go look at our cargo.toml and see if we did anything special there. Oh, we did. Look at this mess. Let's just copy all this. Copy all of this, actually. Then we'll go to our cargo.toml, and we will paste this mess in here. Now we've got a libc dependency on libc. It probably needs to be upgraded, but it's fine. And we've told it, if you panic, don't try to do anything special. Just call our panic handler. That's what panic equals abort means. So we needed that. Let's see if it'll build now. It will. So let's run it. Look at that. It prints hello world just like we wanted it to. I don't think we need either of these. These are both optimization arguments that probably we can do without. Oh, comment executed abnormally with code 14. That's interesting. That means that our program printed hello world all right, but it didn't exit with the right exit status. So let's fix that. So I'm going to get rid of this since it's not important. I'm going to fix this. by calling libc exit 0. I didn't think I needed to do that, but apparently I do now. All right, we'll change the indentation. This just sets the exit status. We call underbar exit because reasons. And now it should run with correct status. It does. It's like fine. So now we've managed to write a program running on my Linux box without using Rust standard library. Is it a giant mess? Absolutely a giant mess. No, the exit, all the functions in libc are unsafe, actually. Because you're calling C code, Rust considers that an unsafe thing to do. It doesn't feel like it should be unsafe, but it is, just by definition. We should talk about the unsafe keyword for a second, because that's a great question. Because this is the first time I think that we've seen the unsafe keyword. Unsafe in Rust means turn off just a tiny bit of the checks that the compiler does at compile time to keep things safe. And by safe here, I mean this. If your program contains no unsafe keyword anywhere in it, then it can only do one of two things. It can run normally, or it can panic. It's guaranteed that those are the only two things it can do. At compile time, we check and prove that when you run the program, it can only either complete or do a controlled panic. Those are the only two possible behaviors of your program. Once you introduce unsafe, then it's possible that you could do things inside unsafe that would cause your program to do weird stuff instead of those things. It could erase your disk. It could, scribble all over your screen. It could do whatever, right? Most normally what it would do is, in an environment with an operating system, is cause that operating system to kill your program because it's doing something stupid. But in embedded world, where we're about to go after the break, there is no operating system to kill your program if it does something stupid. And so unsafe becomes something you've got to be really careful with. So why are these calls to write and exit unsafe? They are unsafe because, like I say, Rust considers calling into any C library or any other library written in C to just be unsafe. Any foreign function interface use is unsafe because you don't know what that code will do, right? The proofs aren't carried out for write. The proofs aren't carried out for exit, that everything's going to be okay. So it's possible when I call write or when I call exit, the program will erase my disk or whatever if I don't call it right. So here inside unsafe, your responsibility is to make sure that these arguments are right, that you call it right. And that's on you. And if you pass bad arguments, probably what will happen is that the libc write routine will just do something horrible that you didn't expect. And so that's what the unsafe keyword's about. That's a great topic to talk about for sure. And we'll be using a little unsafe in our embedded code, but honestly, not as much as you think. We'll be using tiny amounts. All right, so that's our first no standard program. It's not very complicated. If we run it with release, if we build it with release, we get an x86 executable still. And what you find out is it's tiny. If we compile our hello Without that, we'll get like a megabyte of executable code. Most of that code is going to be the standard library. It's not going to be our program at all. And when people say, oh, Rust executables are big, well, yeah, because standard library. And when they say Rust executables take a long time to compile, actually, a lot of times they just take a long time to link, to combine with the standard library. And so here, we've got something beautiful in a way, but also terrible in a way, because we've used a bunch of unsafe code, and we've had to call library routines that aren't portable and blah, blah. So in writing normal people Rust code, we write it with the standard library. But we're about to start writing embedded Rust code. And so we are going to want to write without the standard library. And this, 1,323 bytes of program plus 552 bytes of data is absolutely fine for our tiny, tiny microcontroller. But of course, if I try to run this program on the tiny, tiny microcontroller, it won't work because the instruction set is wrong. We've compiled for L64-bit x86 64, and our little microcontroller is an 32-bit ARM instruction set. So let's take 5 minutes, and at the hour we'll come back and we'll talk for a little bit about the actual microcontroller. We'll run our first program on the microcontroller, and we'll see what that looks like. And in the process, we'll talk about what environment you need to set up for that, and we'll talk about how the compilation process works for compiling on this machine for that microcontroller. Notice that this machine's way too, the microcontroller itself, we can't run the Rust compiler on that. It's way too big. We can run it on here and compile code that we can then run. And I'll show you how to do that. So let's take 4 minutes, and then back at the hour, we will go ahead and pick up where we left off. Sounds good? All right, I'll see you in a minute. Okay, let's see if we can get the volume reasonable. Looks like we can. Looks fine. Okay. Everybody can hear me okay, I guess, and we are off again. So, yeah, we're now pretty much done with the process of messing around with our host computer, with the computer we're going to be using for development. Rust runs on there great, but as we've seen, we need to do something to actually be able to run Rust on our little microcontroller. And so let's just go ahead and do the obvious thing. At this point, I should point out that we're going to be starting in essentially with this. Rust embedded .b2. There's a link from that in that repo that you already have been linked to, but this is the book. This is the book that we're going to be working through for the rest of the time, essentially. We'll be sort of following it. And the first chapter we'll start working with is this, which is setting up a development environment. And I'm not going to go through this for all the operating systems or even go very carefully through it at all. What you need to do is go to this book at some point. It can be now or after class with a microbit 2 nearby to try stuff out. I think most of you should have access to a microbit 2 at this point, and that's great. If not, talk to Mordecai and the West Africa folks and see if you can figure something out. And what we're going to do is we're going to set up a dev environment for this thing. And let me just show you what the pieces are that are in that. Again, I'm working on a Linux box. You can work on a Mac. You can work on Windows. I think you can probably work on Android, but I've never tried it and don't know how. So you just need some machine big enough to compile this stuff. So let's take our thing. I'm going to say cargo clean because I really, really don't want to copy this. What I'm going to do is just this thing. So let's go look at, let's just try to compile our program for the microbit. So again, first of all, you need the microbit probably, and ideally it's set up with a and it will need to be plugged in with a USB cable to whatever machine you're compiling on. And that's all you need. There's no other setup needed. The board itself handles getting code onto it. We'll talk about that in a second. So if you have that set up, then you are good to go. And what we're going to do is we're going to try to, first of all, you'll need a thing called ProBars. And ProBars is a thing that you get. So here's a bunch of stuff you're supposed to install. You don't need to worry about it right now. We don't need debugger yet, so don't worry about it. But what you do need, for Linux, you need to set up udev and check permissions, blah, blah, blah. By the way, we've talked about this before. You may choose to use VS Code or IntelliJ or something. I'm going to skip back over this for a minute. So we said we need a processor. It turns out that the processor we have runs in an ARM instruction set that's called the thumb instruction set because it's compressed. It's a dumb name. And so this is thumb v7, and it's none, meaning there's no operating system. And the ABI has hardware floating point. Believe it or not, there's a floating point unit on this tiny microcontroller, but there we are. So how do I get that? Well, Rust up is presumably how you installed Rust. Rust up target list gives you a list of all the computers you can, all the instruction sets the Rust compiler can compile for. There's a couple of them, but a lot of them are very much the same. These ones in bold are ones where I've actually installed that tool chain for some reason. That also says installed. And so we're going to need to make sure that the thumb v7 em none eabi hf is installed. I don't know why those other ones are even installed actually. So let's explain that that's just done with the obvious thing. You say rust up target install, and then you give the target name. So you'll need to do this. You'll need to do that, and it says, oh, you've already got it installed. But if it's you, it may actually download a bunch. Rust up may actually download a bunch of stuff so that rustc knows how to compile for that platform. And now let's just try to compile our program with that instruction set. And that's as easy as cargo build. We'll do -- release target. What I just said, thumb v7 em none eabi hf. And that's cross compilation. Now we should get an executable that runs on our board, except we won't. Oh. The problem here is that there's no libc. Libc is a crate that is a library that talks to an operating system. And there again, we've got no operating system. We told the Rust compiler we have no operating system. And so the libc crate's like, nah, that isn't what you wanted. Well, dang. We're going to need some way to write our hello world, and this isn't it. Notice that most of the stuff worked fine. It was just the stupid libc calls that didn't work fine. And so the question is, how the heck do we get a binary that actually prints hello world? And what does that even mean? Right? If you look at our setup, right, where is it going to print it? I don't see any display on the back. These LEDs on the front are not going to be the greatest hello world printing place ever. And besides, I need some code that did that, and it sounds hard. So let's talk a little bit about what we're going to do instead. So if you go to if you go to our book code, let's grab some code that should actually work.
Hello, Professor Bart. I think you have not switched to the other screen.
Oh, you're right. I've done it again. Thank you. All right. So let's go over here and look in the book code. And we'll replace our code that we got that didn't work with this code that might. What does this look like? We can not worry about this. This is stupid. Yeah. All right. Let's replace this with something more fun. Because I really want to print hello world here. So let's print hello world. And we'll talk about the pieces of this program, and then we'll be out of time today. Let's see. What I want to do here is in my cargo.toml, I want to get rid of libc because I can't use libc. It's not a thing. And I'm going to get rid of this for reasons I'm about to explain. And then I'm going to start adding some crates. Sorry, I'm having a moment of blanking here. Let me go look. All right, this is the Panic RTT crate, which adds a whole bunch of other crates. And if I look at my cargo.toml now, you'll notice that it's added this crate dependency. What does that do? It tells Cargo, when you compile this program, don't go download Panic RTT from crates.io, and then provide it to our program. The other one I want is the other RTT crate that I can't think of the name of right now. It's RTT target, right? Okay. And what we're going to do here is copy this line as well, foreground. So now let's, if we look at cargo.toml now, it's got RTT target as a dependency. And now if we go to our main program, whoops, what is that from? We can see that we have some things. I need to add the Cortex M crate and the Cortex MRT crate. I'm not going to use the microbit crate right now, but I am going to use that thing I copied. Now, let's try this. We'll initialize printing. And then we will do this. So what's going on here? Let's see if this builds. Yeah, that should be, oh. Side. Unfortunately, I need a feature, cargo features. There's so much to learn. A cargo feature modifies the way the crate is compiled, the library is compiled. So here we're going to compile, we're going to get the Cortex M library and compile it. We're going to tell it, this is a thing you need to do. RTT is our replacement for libc. RTT is a library that lets me print stuff. And I will in a second show you how that works. Let's do this thing. Let's see. I don't think I need the microbit crate for anything, so I'm going to leave it out for a moment. Target. So now it's going to build all these, download and build all these crates. Oops, it's not a function. It's not wrong. I always make that mistake. It's a macro. All right. Oh, no, I wanted panic RTT. There we go. Right. Now we're running into the next adventure, which is that the linker is complaining with this. So we're not getting this library linked right. Whoops. Oh, that's another thing we should fix. Okay, so now we have to fix the linker stuff. And I think the way we did that is we need to probably just add the microbit crate like they did and use it. That's the easiest way. Linking is a nightmare in this setup. This may not fix it. Actually, this won't fix it. Trying to think how to do this short of the ugly way, but I think we might be stuck with the ugly way. Let's try it without the all right. Thinking. I think what I want to do is just give up and do the dumb thing. So we're going to make a .cargo directory, and this gives some special instructions to cargo about how to build our stuff. First of all, it says build for our instruction set. We can quit typing -- target. And when we have that target, two things. We're going to make sure we use the right linker, and we're going to give it this special argument called a linker script that makes sure linking is done the right way. And then when we actually do cargo run, it will run it by downloading it to our processor and then running it. So let's try it. Cargo build. Nope. Memory.x is not anywhere because we didn't include the microbit crate. All right. The linker script thing is a complete nightmare, but this should actually fix it. Nope. Nope. Why is it giving me this? Why? Of course, the joy of live demos is striking me today. Let's take a look at this and see where we've gone wrong. I'm going to replace this with the panic halt crate, which will probably solve the problem, actually. We'll get there. Okay. Interesting. One of those days. Let's do it this way for now. We'll fix it later. So I know this stuff builds. Oh, I see. There we go. Panic RTT target. Oh, I just used the wrong crate. Oh god. I just used the wrong crate. There we go. That should solve the problem. Yeah, we'll get rid of the panic halt crate, which is not useful. Sorry, I don't normally have this kind of trouble. No, interrupt vectors are missing. Okay. Super, super weird. All right, one more time. If that doesn't work, we'll go run the stuff that I know works, and we'll call it a day. I am going to get something running today. You watch me. It's going to be a thing. Okay. One of the things with embedded is it's very common to run into weird little stub your toes stuff. And that is just the way things go sometimes. All right. Let's deal with it. Build. Huh. Oh, it's probably because the pack crate is missing. Yeah, it is. All right. I know how to fix it now. Anyway, all right. Let's look at what we did here. This is what I was trying to show you. This is a normal looking embedded rest for the microbit program. Because of our .cargo/config.toml, it's built it for our instruction set. And if I look in nope, that's wrong. Target / thumb v7, the other architecture. I'll find something called light it up. And that thing is a ARM binary, a 32-bit ARM binary with some instruction set, just like we're supposed to have. So now what you need is this ProBars tool, and the book contains instructions about how to install the ProBars tool. And the ProBars tool is the thing that uploads your program to the microbit via the serial port and starts it running. So if I replace this build with a run, and I flip this board over, flip this board over, if I can manage that. God, what a day. Okay, there we go. No, still not very good. Let's try it like this. That's good. Let me switch to the view where you can see everything. And when we run this guy, he should just work. It runs ProBars, it uploads it to the board. You can see it flashing, and you saw that LED come on. All right. So we are good. We are absolutely good. All right. Let's go back and fix real fast the program we were actually trying to run. No, that should already be included, though. I guess I just need to use the microbit crate. All right. And then we'll make sure it gets used. This is the trick that we used before to get this to link. And that will include the peripheral access crate that makes this all work, I think. One last try then. Look at that! Our Hello World works. And all it took was fiddling around forever. Yeah, absolutely. Cross-compiling, isn't enough, right? It's necessary, but yeah, the way to fix that, by the way, in your case, is to use a different target. Try the muscle libc. MUSL, the MUSL targets are statically linked, and so they don't link against libc. They link against a different libc called muscle, and that can solve that problem. So let's talk about what we've just done after a lot more fiddling around than I thought it would be. We have cross-compiled this program to produce an ARM target. You can see it here. It's in this thumb v7 emnun eabihf directory. In the release subdirectory is our mb2 hello. And you'll notice that it's an ARM executable. It's 7 kbytes, which is fine. Let's look at the source code. And then we've loaded it using ProBars, right? We can actually see the ProBars command we used. ProBars run dash blah, 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 right? So that was shorthand. Cargo run was shorthand for this. Whoop. And it works fine. Notice that this is programmed into flash memory, meaning no matter what powering it off doesn't reset it, right? If I just if I power this board off and power it on again, it will run the Hello World program again. ProBars includes a thing that connects to the board via the USB port after it's uploaded the code. And when our println is called in our program, then that is sent up to the host, up to us on our desktop or laptop. And that's where we get this message. This is really useful for debugging and stuff, but of course, only if it's connected to a host via ProBars. An interesting thing about this, what is returns bang? That's strange. Well, what returns bang means is that main never returns. And that makes sense if you think about it, because what would it return to? It would return to the operating system, but there is no operating system. Your program must never return, so we declare it to never return. And then the compiler checks that. Down here, we're looping, just doing nothing. That's what asm not means, is just do nothing forever, over and over in a loop. If I get rid of that, which is kind of what you'd think you'd write, the compiler's going to complain at me. It's going to say, you know what? You said you weren't going to return, and then you fell off the end. Sorry, that's not okay. So this is one of the joys of Rust, is the compiler really tries to have your back. So this is about as simple as these programs get. We'll talk later about why we need these uses underbar things. And these things are maybe obvious, asm to get the asm, and entry to get the entry thing that actually sets this up to be the place where our program starts. We've now written our first Rust embedded program. We've even made it compile. I think that's all we have time for today. I will commit all this, and we will deal with it. And then on Monday, I hope, assuming if I will try to show up on Monday at our regular time. I will be from China late at night. The Great Firewall may bother us. If it does, my apologies. I will do the best I can to be here. So I hope to talk to you soon. Yeah?
Yeah, guys. Thank you very much for today. It was
Happy
really
to do
nice.
it.
It was really nice having you guys, and then we'll see you guys on Monday. Same time, 5 p.m. GMT +1, and Professor Brad time in China. I don't know what it's going to be by that time. And also, you can check. I pin on the Rust embedded the discovery book. This will guide you to the installation of all you need to start, like for different operating system, the installation of what you need for all the different operating system, and then that will make it more easier. And I will try as much as possible, maybe within the week, to do like a 15-minute video showing on how to go. I know a lot of people are using Windows operating system to showing the process of installing it from scratch in the Windows operating system, uploading it before the next class, so that everybody have the installation, everything running, and then start the next class. Job like they're just writing code and just compiling to the board and everything. So once again, thank you very much, and God bless you for coming. Bye-bye.
Yeah. Don't forget that we have the Rust Edu Zulip. And you're welcome to join our thing. And if you have questions, don't hesitate to ask there. I will talk to you soon. Take care.